In today's lesson, we're going to visit about vectors. A vector is defined as an object that has both a length and a direction. Geometrically, a vector can be represented by an arrow that has a fixed length and indicates a direction. If starting at point A, which is going to be at the tail, a vector, which means carrier in Latin, moves towards point B, which we write as AB, and B is heading towards the head of the vector. A vector may be indicated using a single letter in boldface type like U, or by capping the letter representing the vector with an arrow like U with the arrow across the top. Draw a vector that represents the movement from point P, -1, 2, to the point Q. So if I'm starting at point P, which is -1, 2, I'll start by drawing here. And Q is heading towards 3, 3, which is here. Drawing my arrow this direction, the following from point P to point Q. Draw a vector V that travels from the origin to point 3, 5. So starting at the origin is my starting position, and it goes to the point 3, 5 up here. Of course, it overlaps with Q. And we'll call this V with the arrow across the top. Adding vectors geometrically. To add vectors geometrically, we first start off by drawing vector V, starting from the end of vector U, and the sum of the two, the sum of the U vector plus the V vector, is the vector from the beginning of U to the end of V, giving us vector W. From its starting point to its ending point is the sum of the vectors. We're also able to scale vectors geometrically. To geometrically scale a vector by a constant, we're going to scale the length of the vector by the constant itself. Scaling a vector by a negative constant will reverse the direction of the vector. So let's say we've got vector U here. Given the vector, show three times vector U. So I'm going to give myself a little bit of room here. And I'm going to try to replicate completing it once, twice, and 3 times. So this would represent 3 times vector U. Now, the opposite of vector U would be to go the opposite direction 1 time. So this would be negative U vector. And then you probably guessed it, -2U would be going backwards twice. I know it's not exact. I don't have an exact ruler to measure it, but we get the idea. Given the specific vectors where U is pointed upwards and vector V is pointed towards the right, show and draw vector U minus vector V. So I'm first going to start off by drawing vector U as if I were going to add these together. Trying to replicate as best I can here. And then vector -V, well, V is going the direction up and to the right. So -V would be starting where we ended with vector U, going the opposite direction 1 time. And this place here, where vector V ends, this location here, is U minus V. A vector can be described by its magnitude or its length. The absolute value of the vector and an angle theta. A vector with length 1 is called the unit vector. We can also write a vector in component form, which represents the vector using 2 components, the x component and the y component. This indicates the vector represents the displacement of x units horizontally and y units vertically. We're also going to define and see that the magnitude of the vector as the length of the hypotenuse of the right triangle, or in polar form, the radius r. So magnitude, I'm going to underline, is the length of the hypotenuse of the right triangle. Or, of course, the radius r if we're in polar form. So let's talk about some alternate notation for vector components. Sometimes we may see vectors written as a combination of unit vectors I and j, where I is the point to the right and j is the point upwards. In other words, I is the component vector 1, 0, and j is 0, 1. In this notation, the vector u, 3, negative 4, can be written as 3 vector I minus 4 vector j. Since both indicate a displacement of 3 units to the right and 4 units down. So just different ways in which we can create the vector. So I can write it using this component form, or I can write it with I and j. Both are equally as great. Find the component form of a vector with length 7 at an angle of 135 degrees. So I know that the length is 7, so that's also going to be my radius of 7, because that's the vector length is the magnitude of the hypotenuse. But we are at an angle of 135 degrees. So if I want to find the component form, I need x and I need y. We know that x can be found by taking the radius of 7, or the hypotenuse, times cosine of the degree value. And we know that 135 degrees at cosine is negative square root 2 over 2. So this would be taking 7 times negative square root 2 over 2, or just negative 7 square root 2 over 2. Our y value can be found by taking the radius of 7 times sine of 135 degrees. And sine of 135 degrees is positive square root 2 over 2, which is just 7 square roots 2 over 2. So we could write this in component form such as negative 7 square root 2 over 2 and 7 square root 2 over 2. Or if I'd like to use I and j, I'll put or because both of these are equivalent. Negative 7 square root 2 over 2i plus, since it's a positive, 7 square root 2 over 2j. Find the magnitude and angle theta represented by the vector 3, negative 2. We know that the magnitude represents the hypotenuse, or the radius. I also know that radius squared can be found by taking our x squared plus our y squared. From the component form, I can say that radius squared is 3 squared plus negative 2 squared, or r squared is 9 plus 4, where r is the square root of 13. I'm only given x and y. I don't know what theta is yet. I know I am given the radius as well, but since I was originally given x and y, we haven't utilized tangent in a while. So I can find our theta because I know tangent is our y value over our x value, and in this case, negative 2 over 3. I don't have anywhere on the unit circle where tangent is negative 2, 3. So in order to find theta, we know we need to use the inverse. The inverse of tangent at negative 2/3, which is going to give us approximately negative 33.69 degrees, we're probably going to want a positive theta value. So we know this is coterminal with negative 33.69 degrees. If I add one rotation around the circle, our degree value is 326.31. So we've also found theta. So we found the magnitude, which is also the hypotenuse or radius, and we found theta at approximately 326.31 degrees. An object is launched with an initial velocity of 200 meters per second at an angle of 30 degrees. Find the initial horizontal and vertical velocities. Okay, so we know a couple of things here. I know that I'm traveling and I'm launched at 200 meters per second at an angle of 30 degrees. So I know the angle in which I am shooting something off here or launching it, and that I'm going 200 meters per second. I'm trying to find the horizontal and vertical velocities, which would be our x and our y value using vectors. We know that x is going to be, so if we're up here somewhere, we kind of drop down that component there. I know my x value is my radius or my hypotenuse of 200 times cosine the degree in which I'm angling at is 30. And this, of course, is 200 times the square root of 3 over 2, which gives me approximately 173.2 meters per second. And my vertical is going to be 200 times sine of 30 degrees, which equals 200 sine of 30 degrees is half, or approximately 100 meters per second. So our horizontal velocity is 173.2 meters per second, and our vertical velocity is 100 meters per second. Of course, gravity and wind and all those things will play a role, but we're assuming that that's not intentional right now. We can combine vectors in component form, just as kind of you would expect to be able to do. So if we're in component form and I've got two different vectors, I can add them together, adding together the x components and adding together the y components. Similarly, I can subtract the two vectors by subtracting the x components and subtracting the y components, or multiply by any constant by multiplying each component by that constant. So let's say I'm given vector u and vector v. Find a new vector w that is 3 times vector u minus 2 times vector v. So I'm going to write this out as 3 times vector u, which is 3, negative 2, minus 2 times vector v of negative 1, 4. And I can multiply each piece of the component by 3 in my first vector, giving me 9, negative 6. Subtract, so I'm just going to put in the 2 here, and I'll come do that subtraction in a moment. Negative 2, 8. Okay, now we'll subtract the components. I'll take 9 minus negative 2. 9 minus negative 2, of course, is 11. Negative 6 minus 8 is negative 14. And I have found my new vector w. A woman leaves home, walks 3 miles north, then 2 miles southeast. How far is she from home, and what direction would she need to walk to return home? How far has she worked by the time she gets home? So if we're starting to walk due north, our north component is 0, 3. Then she moves southeast 2 miles. And then we have to do we have to answer all the other questions. So let's also talk about what that means if I am moving southeast. Drawing a little picture here. I'm going to put a vector at southeast. So I know I started up here at 0, 3, went north, and then I went southeast. But let's assume I'm starting here. What do I know about going southeast? I know that to cut this vector, or this in half, this would have to be 45 degrees, or negative 45 degrees, excuse me. So then all the way around, the direction of this vector is 315 degrees. We're going to assume she's walking perfectly southeast. I know that this ending point here is square root 2 over 2, negative square root 2 over 2, according to our unit circle. I know that I've gone 2 miles, so I know that the length of this is 2 miles. In order to combine with the north one, I need this also to be in vector form. So I'm going to do that by saying 2 times cosine of 315 degrees is my x component, and our y component is 2 times sine of 315 degrees. From here, again, I know that cosine of 315 degrees is square root 2 over 2, and I know that sine is negative square root 2 over 2. So I will replace these as best I can here. So 2 times square root 2 over 2, 2 times negative square root 2 over 2. Well, if I'm going to end up combining it with my north, I will need to put these component forms. Let's put them into decimals. When I multiply, I'll get 1.414 and negative 1.414. So ideally what's happened is that we have walked 3 miles north. From here, we have then walked southeast 2 miles. We want to know how far we are over here. So we want to add our vectors together. And it's not as simple as 3 plus 2. I know that so far she's walked 3 miles, so 5 miles altogether, but how far from home and at what direction does she need to return, and then how far has she walked by the time she gets home. So in order to find this location, this vector, where we can find the angle at which we're at, we'll need to add these together. So we went from north. I'm going to add that to vector, the southeast vector. And this gives me vector 1.414, 1.586. So then the question is, well, how far from home are we? I know that I can find the length of this by finding the, we know that this is x and y using the distance formula. So the length of the distance between these would be the square root of 1.414 squared plus 1.586 squared. And this, again, plopping that into our calculator to help us will be approximately 2.125. Well, what direction are we? I've got 2 vectors, so I have an x and I have a y. I don't know what theta is, but since I have x and y, we can use tangent like we had done before. I know that tangent, if I want to find theta, is 1.586 over 1.414. So therefore, finding our theta, we need the inverse tangent. Which is going to give us approximately 48.275 degrees. And 48.275 degrees is in the first quadrant, so we would be heading northeast. Thus, in order to return home, we need to flip around and do a whole 180. We need to take 180 degrees and go back the opposite direction that we are headed, because that would be towards home. So 228.273 degrees is the direction we need in order to return home, because we were facing northeast. And in order to find the total distance, so we want to find the total distance she's walked altogether. Well, we first started going 3 miles, then we went 2 miles, and then our walk home we determined was 2.125. So then altogether she will have walked 7.125 miles. So again, this is how far we are. This is the direction we were headed. We need to turn around and go the opposite direction. So we add 180. So we're facing the opposite direction. So we're going to head in 228 southwest, of course, degrees southwest. And altogether, from our starting point to the ending point of our trip, we have done 7.125 miles. In a scavenger hunt, directions are given to find a buried treasure. From a starting point at a flagpole, you must walk 30 feet east, turn 30 degrees to the north, and travel 50 feet. And then turn due south and travel 75 feet. Sketch a picture of these vectors, find their components, and calculate how far and in what direction you must travel if instead you want to go directly to the treasure instead of following the map. So let's assume that, let's start here. And this is going to be the flagpole. It says that we're going to travel 30 feet east. So just heading east, and we've traveled 30 feet. Then we're going to turn 30 degrees to the north and travel 50 feet. So if I were to continue on this direction but head 30 degrees, we're going to go this way. So here to here is 30 degrees, and then we've traveled 50 feet. From here, we're going to turn due south. So I should just point this all the way down, and we're going to go 75 feet. And this is where the treasure is. We want to know what direction should we head in order to go directly to the treasure, and then of course, how far away is that treasure? So the component of our first vector, we'll call it V1 since it's our first one. Our first vector is the component of 30, 0. Because I went 30 degrees to the right and I'm not going up or down. Vector 2, however, is a little different. Our second stop, we had to turn 30 degrees, but we're still traveling a length of 50. So our x component is 50 times cosine of 30 degrees and 50 times sine of 30 degrees. We'll worry about them later. And then our other one, our last vector, we are just heading south. We're not going left or right or in any specific direction. So vector 3 is just 0, negative 75, since we're going negative units. In order to get to the flagpole, we know that if we have vectors, the addition property says if we add all the vectors together, it's from the starting point, we can add them all up, to the ending point, and that is the direction we're going. So I'm going to call this vector flagpole. So vector F is equal to adding all the components of our vectors together. So 30 plus 50 cosine of 30 degrees plus 0. And our y components, 0 plus 50 sine of 30 degrees minus 75. Since we know we're going to end up with a bunch of decimals, since the sine and cosine of 30 degrees aren't very necessarily friendly, I will use my calculator to find 50 times cosine of 30 degrees plus 30 gives me 73.301. And 0 plus 50 times sine of 30 degrees on my calculator minus 75 is negative 50. So what is the length of this vector? How far is it from the flagpole to the treasure itself? Our length can be found by taking the square root of each of these components squared. Again, we know that radius squared is equal to x squared plus y squared. And we'll get approximately 88.73 feet. So it's about 88.73 feet from the flagpole to the treasure. But at what angle do we need to go? What angle do we need to go? I know x, I know y. Let's use that tangent again to help us out. I know tangent is the same as our y value over our x value. And if I want to find theta, we're going to plop into our calculator the inverse of tangent of negative 50 over 73.301. And we'll get approximately negative 34.29 degrees. We know that that's going clockwise, so we will be heading 34.29 degrees southeast. So if I put the directional piece, I don't need that negative, or this part tells me that I'm going clockwise. We could also add 360 degrees to make it positive, and then we would know where we were specifically in that third quadrant. In our last example for this lesson, three forces are acting on an object as shown below, each measured in newtons. What force must be exerted to keep the object in equilibrium? This means that the sum of the forces is equal to 0. First of all, I'm going to write each vector in its component form. We are given some degree values, so I'll start with this 6 Newton one. We're going to take 6, which is the length of the vector, times cosine of the degree the vector is at, so 30 degrees, and 6 times sine of 30 degrees. Now, I am able to evaluate cosine of 30 degrees and sine of 30 degrees, so I will do that. I'll have then 6 times square root of 3 over 2, 6 times 1/2. Simplifying, I now have the component 3, square root 3, and 3. The component of 7 newtons, we're going exactly left here, so we're going to have the component of negative 7, 0, because there's no angle that it's justifying here. However, our 4 Newton is going downward, of course, but we are at a specific degree value of 300. So the length is 4 times cosine of 300 degrees and 4 times sine of 300 degrees. I am able to evaluate because sine and cosine of 300 degrees is on our unit circle. 4 times 1/2, 4 times negative square root 3 over 2, which of course reduces to 2 negative 2 square root 3 as our components. It tells us in this line here that the sum of these three forces is 0, means that it's equilibrium. So I'm going to add each one of these forces together, so each one of these component forms together, and set it equal to 0. But we don't know what that that force is. So we have to add all of the forces together plus an unknown force that we're trying to find. Therefore, I'll add 3 square root 3 plus negative 7, 0, plus 2 negative 2 square root 3, plus our unknown force, we're not sure what that is yet, but we're going to solve for that, is equal to 0, because all the forces added together are 0. When I add the first parts of all of my components together, I of course will have 3 square root 3 minus 5. And then I'll have 3 minus 2 square root 3. Plus, of course, x, y, our unknown force, still has to equal 0. I am allowed to subtract vectors, so I will get xy by itself and set this equal to 0, 0 minus vector 3 square root 3 minus 5, 3 minus 2 square root 3. And now I just have two vectors that I can subtract. Xy then is equal to negative 3 square root 3 plus 5 and negative 3 plus 2 square root 3. We certainly could turn these into decimals if we want a more rounded answer. Negative 0.196, 0.464. This is the force needed. To create an equilibrium. Now, we found the answer to the question. However, we could also find the magnitude, so we could find how long that vector needs to be. Also, we could find the angle at which this vector is located by using the inverse tangent as we had done in previous examples. It's not asking for that, but we certainly could go the extra length. We could find magnitude by finding the magnitude of this vector, and we also could find the inverse of tangent to find what angle this force is to add it to the picture above if needed.